In this video, we're building a powerful, fully 3D printed RC drift car controlled with Arduino boards, has 4-wheel drive, and the ability to slide around corners with a cool smoke effect. To control it, we'll be using the Arduino transmitter and receiver from the last video. And to build the car, we'll need its components and materials, which you can find listed in the video description. Taking you through how I designed the car, I started from obtaining precise dimensions of every single component and modeled them into the 3D design software I use, known as Fusion 360. The modeled parts helped me best visualize and model the chassis with the right measurements to fit them all in and create every little moving part which goes with the chassis, as well as decorative features to give it the drift car look. With the drift car design complete, you too can now 3D print the drift car by purchasing its 3D model files listed on my Cults 3D page with print settings and more info to guide you on 3D printing the parts right. Click the link in the description below. Once you have the files, you'll need to lay them out and prepare the G-code files in your 3D printing software. Then begin printing out the parts in 2 batches with the color of your choice. Please excuse the nasty stringing on the prints due to not storing my filament properly. Since the humidity has really caught up, I'll begin using a filament dryer for all my future prints. After some cleanup, here's how the parts turned out. We should have wheels, gears, links, axle joints, the chassis, supports, and decorative parts. With a soldering iron, we can begin melting in 27 of these M3 threaded inserts into the car parts that need them. Now we can begin installing the first part of the drivetrain, which is the rear drive mechanism. Let's pop in a 9mm bearing into the chassis, which supports the drive shaft. Then attach the 2 10mm bearings onto one of these beveled spur gears without a differential, followed by assembling the rear drive pinion gear with a bearing and spur gear attached with which the motor makes contact. We can then install it and the spur gear positioned with orientation in mind. Afterward, let's secure the rear gearbox housing together and install the brushless motor with its pinion gear to wear in the bevel gears inside, which will help make the shaft turn with ease. Next, we can assemble the front drive gears, which take the motor input through a drive shaft which connects to the front pinion gear that is strengthened with super glue. We can then attach bearings onto these gears like the last and put them in place with the orientation of the spur gear in mind so it rotates with the same direction as the front. For the drive shaft that connects the front and rear drive gears, we'll need a 2.5mm stainless steel shaft that is marked so it's cut down to 124mm in length, and for the front and rear axles, a couple of shorter 19.5mm sections. With the help of a bench vise, let's cut these marked pieces of steel to end up with the 3 sections. And using a file, we'll begin completely filing down the shorter ones into halves, followed by marking the ends of the longer rod and filing them down halfway so the flat ends match the lengths of the front and rear pinion gears. Now let's work on installing these axles and the drive shaft into the gears through heating up the rod ends and carefully pushing in the rods without splitting them. However, with the front pinion gear, you may need to first wear in the connection with another axle and then slide it on with a more loose fit to the drive shaft once it is in place. Again, we'll wear in the gears for smoother rotation, now having the front ones installed. For the front and rear axles, we'll push in a shorter rod into each spur gear so an input shaft cup can firmly connect to each end. However, I still recommend securing these on with the addition of super glue. Now these two can be secured into their gearboxes with the corresponding upper housing pieces, closing them up with the help of some M3 screws. Next up, let's install the swing arms, which are designed to help hold the wheels. We'll need to make the two fork pieces that secure them, which consist of a tab with a couple of 2mm bicycle spoke pieces pushed into each. With the help of each, the swing arms can slide onto the fork parts and then into the chassis. However, the front fork gets secured with the front bumper holder using the longest bolts in your M3 screws kit. Keep in mind that it actually needs to be installed with the flat side facing up. So now we can install the wheel cups, which hold the wheels through bearings. You have two for the rear and two for the front, which hinge side to side. We'll cut a 10mm section of 1.5mm sweet wire rod for each wheel cup. Each one gets pushed in and is secured with super glue within the wheel cups themselves to allow them to hinge up and down. The only difference with the front ones is that they're screwed on so they can additionally hinge side to side for steering. We can then push in the smaller 9mm bearings into the wheel cups with a tight fit. For the universal joint drive shafts, if made out of PLA, each one of these dog bone looking pieces needs to be fully coated in superglue to prevent it from breaking when under tension. We can then cut an 8mm section of paperclip wire, which gets pushed into its ball hole for grip. Then with some more paperclip wire, we can adjoin the dog bone piece with the wheel connecting part of the joint through one of these little cubes. The dog bone takes a full-length piece of wire holding the cube, while the other joint piece connects with two shorter pieces of wire pushed into the cube from each side, forming the universal joint. Each wire end can then be superglued to stay put. Now we repeat this 3 more times to have 4 complete universal joint axles, which allow for rotation while bent at different angles. Now let's install these universal joints into the car, connecting the input shaft cups to the bearings. With these installed, the axles should all rotate smoothly. To connect the upper swing arms of the wheel cups, we'll need 4 of these 4.8mm ball screws with their threads cut halfway up, sanded, and installed in the wheel cups while allowing the axles to spin. The upper part of the swing arm consists of an M3 bolt, swing arm piece, and a couple of nuts. 2 of these units screw into each of the gearbox housing arm pieces. For the lower part of the swing arms, we'll need 4 of these ball cups that connect to the ball screws. Each one can be worn in to rotate easier by turning them on a ball screw that's been heated. Now for the linking part to finish the upper swing arms, we'll glue these 10mm sections of paperclip wire. The wheel cups should now be able to stay fixed vertically while moving up and down or when turning. For the shock absorbers, we're using 4 of these tiny 26mm 1/28 scale RC car shocks, which take these included spacers and bolts, then get secured to the chassis onto either of the 2 hole pairs in each spot, attaching the lower swing arms to the upper chassis arms. For the shocks to stay well secured, I recommend using longer bolts with nuts. To complete the steering mechanism, let's take 3 of these ball screws, sand off enough of 2 of them to fit into one wheel cup and one for another cup's arm. We can now make the steering link piece, which consists of the right length of wire and 2 ball cups, which then link the 2 ball screws below. With some paperclip wire, we'll make the servo link, which clips onto the only ball screw sticking up. Now comes the time for installing motors. Starting with the servo motor, since the stock Metal Gear servo doesn't fit into the chassis, we'll need to clip off the 2 tabs to then make it fit. We can follow up with the servo mounting piece, which screws on with a couple of bolts and a ball screw. Then the servo link can get attached to the servo horn at the right distance apart from the left wheel cup with everything pointing straight. The servo link can actually be adjusted a notch up the servo horn for a wider range of steering. For the drive motor, we're using this Rocket RC Mini 3500 kV brushless in-runner motor, which will secure to the chassis with a couple of M2 screws, followed by sliding on its pinion gear onto the chamfered shaft with a tight fit. Now for the smoke effect, we're using a couple of these humidifier modules which emit water vapor from these foam sticks that absorb water. Really fun components to play around with. To set them up, we'll begin by soldering wires to their power module, one for power, another for ground, and the white one for signal so we can remotely trigger the module to turn on. The humidifiers themselves first need their wires desoldered and reinstalled through the chassis of the drift car so the connectors protrude from the top side. Then we can superglue them with the emitting sides facing out. For the underglow effect, we'll be using a couple of LED filament wires or LED strips in wire form that light up. We'll take the pins with the holes and pull each of those through the bottom part of the chassis and glue the ends with only the pins poking out at the surface. Then we'll glue the LED filaments to sit in the tracks and finish off by repeating what we did earlier by gluing the other end. We then repeat this for the other wire. You see, at the surface we should have the cathode and anodes of the LEDs sticking out. So next we're going to wire the 2 water vapor modules together in parallel with one connector. And then do the same thing with the LED filaments, wiring them in parallel only with a wire coming from each end. These LED wires get quite bright at only 3 volts. Next, we can secure the humidifier modules as power supply with the shortest possible screws. So for the underglow LEDs, we'll need to make a custom power supply module that allows us to control the on-off status, which consists of an SI2300 N-channel MOSFET and a surface-mounted 10 kilo ohm pull-down resistor with 3 2 kilo ohm and a couple of 2 20 ohm quarter-watt current-limiting resistors soldered onto a perforated board. The LED's resistors just get soldered in parallel to form a higher watt current-limiting resistor followed by a wire to connect the LEDs, another for ground, and the white one for signal. After trimming the board, it should look more or less like this. Here's a good reference image to clearly see the connections. The LED control board can then be double-sided taped to the chassis and have the cathode LED wire soldered on board. After a bit of wire management, we should have 3 wires sticking out from the LED board and 3 from the humidifier's power module. To control the motor, we'll need a bidirectional brushless ESC that can handle 18 amps or double the current output of the installed motor. We'll simply need to replace its power connector to instead match the one on the battery and then pop it into the chassis where it's designed to sit. Then we'll solder the 3 wires in order to the motor's terminals. The outer 2 can actually be swapped to reverse the motor's rotation. Electronically, all we really need now is the receiver. So next I'll design the drift car's Arduino receiver PCB, replacing the sketchy perforated board on my previous one. To design it, the PCB design software I happen to use is called Flux AI. Starting with the schematic, I'll prompt Flux's AI assistant for the best selection of parts and components to put in the receiver design, then begin searching for the components in Flux's library of parts according to the list it has generated. I'll drop them in one by one, followed by making schematic connections according to the old receiver. From here, I can take the schematic and design a PCB through laying out components and making traces, following the helpful tips from Flux's AI Copilot, which overall helps you choose the best parts for a circuit circuit, spots out wrong connections, and even writes out steps for connections between specific parts. Flux AI as a PCB design software makes designing PCBs a piece of cake by simplifying the whole process and, most importantly, saving you time. With Flux, I designed my Arduino receiver from schematic to PCB in just one day. The AI Copilot helped me achieve a leaner component layout and avoid critical flaws with its immediate feedback. Try out Flux for free today and design your project's PCBs with AI by your side. Click the link in the description below. So to get your hands on this PCB's Gerber file, click the link in the description below to access the project files folder, which includes the free downloadable Gerber file of the receiver PCB, which I designed to simplify the making process so you don't need to worry about connections and instead only focus on soldering the components to achieve a complete receiver. Now we'll need a third-party manufacturer to make the receiver PCB. For that, we're going with JLC PCB, sponsors of this video, which offer you high-quality and low-priced printed circuit boards made based on your designs to create the efficient circuits your projects need. Getting a quote and ordering is quick and hassle-free, like for the PCB of the receiver, where you only need to upload its Gerber file, select the following board parameters such as the number of layers, quantity, thickness, and color. Then at last, submit the order and enjoy fast shipment with the PCBs at your door in a few days. Personally, I'm very pleased with the quality and reliability of these PCBs. But if you need more complex boards for your projects, then JLC PCB's 6-layer PCB capability would be your choice, with the added benefit of free via in-pads. Sign up to get $60 worth of free coupons and give their service a try. Check the link below. So this is how the PCBs turned out based on my design in Flux and created with the help of JLC PCB. We can now begin assembling an Arduino receiver with the components we have laid out onto one of the boards. As with the other components and parts for this project, you can find these listed with product links in the description below. So normally when soldering SMD components onto a PCB, you'd use solder paste, but as I didn't get some prepared, I'll instead use solder flux as paste and soldering tin to bond the components. With the surface mounted components in place, we can begin installing the Arduino Pro Mini, NRF24 radio transceiver, peripheral pin headers, headers for voltage monitoring, analog inputs, power inputs, and for programming. And after a bit of soldering and pin clipping, we have a receiver. The transmitter which will connect to it is this Arduino pistol grip radio transmitter, which used to connect with the Arduino receiver prototype in the last video. The new receiver gets programmed the same way as the old one, with an FTDI USB to serial converter connected to the female pin header. The receiver and transmitter code with more info can be found linked in the last video, which you can find through clicking the link below this video. Once programmed, the receiver can be clipped into place on top of the ESC without adhesives. To wire it, we'll first give the appropriate pin headers to the sets of wires from each module, shorten any if needed, and then plug these into the receiver's headers, starting with the ESC on channel 1, servo on channel 2, then the LEDs and the humidifiers connect to any channels from 5 to 8. Keep in mind that you can find the car's wiring diagram linked with the other project files in the video description. Next, we can mount the 2-cell 500 mAh LiPo battery held down with the clip and body pin. Then for both looks and stability, let's install the car's tail wing and top supporting bar, which prevents the chassis from bending. Onto these crosses which poke out through the bearings, we can finally attach the 3D printed wheels, but first let's give them a little grip by rolling on some electrical tape and cutting off any excess with a hobby knife. Let's also do up the other wheels with the same method. But before we attach the wheels, adding a bit of super glue to the inner edges of the bearings will help prevent axle wobble once the wheels are on. So with the locking feature of the crosses, we can pop on the wheels and secure them from falling off with some small screws. Unlike what you see, I do recommend using ones that are twice as long. This one is optional, but to protect the car from collisions, let's cut out a front bumper with some foam and sandwich it between the bumper plates. To load up the modules, which will create the smoke effect, let's cut up some 3cm sections of that foam stick, soak them, and push them into the cylinders. Now the drift car is complete. If you ever want to give the car a body shell, you can clip one on with body pins to those standoffs with holes on top, but I prefer to keep mine looking the way it is. Pairing the Arduino transmitter to the car is straightforward. You simply switch it on and it automatically binds with the turned on car. With the smoke effect modules connected to channel 7, you flick the lower toggle switch to turn them on and twice up and down to turn them off. Since the underglow LEDs are on channel 5, the upper toggle switches take care of turning them on or off. So before we give the car any drive tests, let's charge her up through the battery's 3-pin header connected to a USB 2-cell LiPo charger. Before we give this cool drift car a blast down my living room tiles, keep in mind that if you're looking to build your own one, don't miss out on reading the full tutorial blog written on the Electra Labs project platform, with images and key takeaways to get your own drift car up and drifting. Check the link in the description below. To perform a drift with the RC car, you turn the steering wheel in the direction you want the car to go as you're hitting the throttle, and you immediately turn the wheel the opposite way to make it slide sideways as it turns. For this to work, you need to make it drive at a higher speed and skid its wheels. It may seem tricky at first, but you get the hang of it. If you wonder why the car has this initial buzz or gear grinding when driven at low RPMs, it's due to the brushless motor being sensorless, which confuses the speed controller on which direction to rotate it, so it instead vibrates. If you know what's the fix to this problem, feel free to comment with your solution. But at least it runs pleasingly smooth when drifting or driving at a decent speed. With a range of up to 100 meters and 10 to 15 minutes of battery life, the car gives you plenty of room and time to drift around. One thing to keep in mind is that if 3D printed PLA gears are used, they'll eventually wear down like this pinion gear did from the motor's heat, and other rotating parts such as the joint axle damaged from high speeds. So I highly suggest having the parts under tension to get either 3D printed from nylon, a tougher plastic, or metal machined from aluminum by JLC with their parts manufacturing service. With stronger materials used, you'll have a long-lasting, thrilling RC car to drift around with. Once again, if you're hyped about building your own 3D printed RC drift car, then consider purchasing the 3D model files to all of the parts. You can find the product page listed in the description below. And maybe even use JLC's 3D printing service to print out your car's parts if you don't yet have a printer. Also, if you're keen on controlling your drift car with an Arduino system like I have, click over here to watch my previous video and learn how to build the Arduino pistol grip transmitter. I'll be waiting over there. See ya, and remember, you can make anything you set your mind to.